if you have done machine translation research at any point in the past 10 years, you probably have seen this website and this matrix with BLEU scores across different languages in the WMT tasks. It's a little bit ugly color scheme wise, but anyway, I'm going to talk about why I'm not happy with that way of evaluating. And in particular, I'm going to say that BLEU sucks. And like, yeah, we all know it's not a great metric for translation. It has issues, but it's not just that it has issues. The issue that I'm going to talk about is that it doesn't actually give something we can compare across languages that well. And it's measuring two things at the same time. That's what we're going to look at in this talk. First of all, why is BLEU not good enough? Why can't we compare it across languages? Well, first of all, it depends on the tokenization of what a word is, right? BLEU looks at 1 grams, 2 grams, 3 grams, 4 grams. So if I do characters, well, then I have very small grams. If I do entire words, I have big grams. And so the tokenization now affects this score. And so if we have English prime, where, I don't know, clitics are split off with a space, we're going to get different BLEU scores. That's really stupid. That can't be right. So that would really make it hard to compare BLEU scores, right? It's become, of course, more obvious once you start to go beyond these thought experiments and actually look at different languages like a good middle of languages like Turkish. We have a highly inflected word that corresponds to 5 English words. So getting this one right in Turkish gives you a 1 gram. That's not worth a whole lot. Getting it right in English gets you 2 4 grams and 3 3 grams and so on. That's a lot. So that's really unfair. We can't compare that nicely. So what we're going to be doing is, again, do the thing we did in the previous paper. Look at the likelihood. Look at the probabilistic output of the probabilistic generation model. Because nowadays a neural machine translation model is often probabilistic, right? It has this output distribution, again, factorized autoregressively left to right, 1 token at a time. And so we get a probability of the output. We get a surprisal of the output given the input. The second one is what I talked about, measuring two things. Because even if we look at this probability, the surprisal of the output given the input, that really measures 2 tasks. One of them is kind of extracting the input, like figuring out what it is that we're talking about. And the other one is actually creating fluent output, creating output that would look good under a language model. And so in this paper, we are saying, let's try to really zoom in on only this translation part. Like, we have just talked about how generation works, right? We've talked about there's differences in generation. German is hard to generate, English is easy to generate. Okay, you know, maybe there's something there. So if we're going to talk about translations, maybe we should just take that out of the equation, correct for that. And that's going to be the intuition of what we're going to be doing. It's going to be a bit fancier than that, and for that, let's just introduce a tiny little bit of notation. Generative models, okay, that's a distribution. Surprisal of likelihood, we've seen that. Bits needed to convey a message. The entropy is the average surprisal, and so the average surprisal really is how surprised do we think we're going to be? How uncertain are we? So entropy is a measure of uncertainty. And what we can do is extend this to 2 random variables, so like a target sentence and a source sentence random variable, connected like that. And so now these concepts still apply very much the same way. So what we can do now is get this conditional entropy. The entropy, the uncertainty over this random variable y, let's say the target languages, given information about the source random variable, so the source language. And so it should make sense that the uncertainty we have over target languages, without knowing the source sentence just yet, is huge. Like, we have no idea what it's going to be about. But if we know the source sentence, we shouldn't be that uncertain about the target anymore. Like, it could still be a number of things. It could still be a number of translations, and we might still struggle to model that nicely. But the space has become much smaller for what is acceptable or for what we should expect. And so taking this uncertainty we had a priori and subtracting the uncertainty we still have left, even after we've seen the source sentence, is really asking, how much did the source sentence help us reduce uncertainty about why? How much information did the source sentence give us? How much information could we extract from the source sentence? And that's exactly what we want to measure. And that in information theory is called mutual information. Now, in this pure case where we are talking about the same probabilistic universe, this is symmetric, right? Assuming that's all with respect to the same joint distribution of input and output sentences. And you might visualize it something like that. If we translate like from source to target, that would be the right side. The uncertainty we have over the target is to some degree uncertainty that just exists because language can be, you can always paraphrase something. So even given the source, there's some uncertainty. But there's also some of the uncertainty that gets removed because we've seen the source. And so that's what we want to measure. Of course, we don't really have this whole distribution. And again, we also want to talk about models. So where do models come in? Well, what we're going to be doing is essentially the same thing, but we're going to be measuring the uncertainty over the target language a priori with a language model. So just as we've done in the talk before, still take this one here to be a machine translation model. And then the difference between those two is what we call cross-mutual information. It's no longer symmetric because we had these weird models Q instead of the true distribution P, with which we are taking the expectation still. So this is just a test data set in this case. But we can now make the statement, you know, how much is uncertainty reduced from targets through the MT model. And so that hopefully tells us something about how easy or hard is it to transfer information? How easily does information flow from input to output? That's what we're going to measure. And that's definitely very opinionated. Like, you might say, well, that's great, but I really care about output quality, so I really want to measure both at the same time. I'm like, yeah, great. You can use BLEU, you can use meter, you can use TR, all these things are out there. You should always use humans anyway. The point is, this is really trying to make you think and realize that there are two tasks going on and ask which of them, specifically about the first one, for which languages is that task, the extracting of information, harder. And so that's really what I want people to take away from this paper. The results are not going to be like, I think this is the interesting part. You may disagree, I don't know. But we can talk about the results. I guess I should, it would be weird not to. We trained a bunch of models, only from English into other languages in Europarl and from these other languages back into English because we didn't have much time or budget. Standard transformers models, BPE with a bunch of merges, nothing particularly surprising there. And the first thing I want to look at is how does our measure of cross-mutual information correlate with BLEU. And so these languages are where we translate from a language that is not English into English. So in that case, the BLEU scores are very much comparable, right? Because the output is the same language with the same tokenization. And so BLEU would be fine to look at differences here, you know, taking apart this different. Sorry, I just lost my train of thought there. It's been a long day. Where did I start from this? Oh yeah, we should find a good correlation. If our metric is going to be any good, then it shouldn't destroy the good that we know BLEU has when we translate into English. So that's nice, they correlate nicely. If we look at the languages that are from English into a different language, they don't correlate quite as nicely. And that, I think, we can take as evidence that comparing BLEU scores across languages is a little bit sketchy. And it really might be an issue in a way that our probabilistic metric is not. Now, we also have a ton more of these plots for how things differently correlate in the paper, and I encourage you to check that out if you want. But really, this is just the main takeaway I'm gonna show here, where we are doing this decomposition of asking if we translate into English. So that is going to be this dashed line over here that you see coming through all the left bars. That is going to be part that is just still uncertainty even after you know the source sentence. So that's going to be the orange part that we get by a language by a translation model. And there's going to be this light blue part that we claim is what we're interested in. It's this cross-mutual information. How well did we transfer information from this foreign language into English? So we see they're different for each of the languages. Definitely knowing the source sentence reduces uncertainty a lot. So the blue thing is bigger than the orange thing, but there's still enough uncertainty left. So the orange thing is still there. And what we can now also do is contrast this with if we take the same pair, but translate from English into that other language, well, oftentimes that's more difficult in terms of just overall surprisal, with the exception of Danish and Swedish, where it's easier altogether. But we can also then see that there is a lot more extraction going on. We have a lot more less uncertainty left in the end. So the takeaway from this is what made us title the paper the way we did. It's easier to translate out of English, so the second direction, than into it. And we say it's easier because these blue bars are bigger, because we have successfully funneled more information from English than we did the other way around. And the reason that we get worse results when translating from English into other languages, we claim, is because of the first paper I talked about, because generation in these languages is harder, not because the extraction of information. The flow really is the difficult part. And so that's why this is, I think, more of a food for thought than like go and measure like this, because no, don't measure like this. Measure in whatever your task asks you to measure in, and probably it should be a human evaluation. But think about that there really are these two components to machine translation with neural models the way we do it. And it might be interesting to look at that. Okay, before I close out, we also looked at correlations. A lot of nope. Yeah, deja vu. We've seen this before. Nothing matters. Life is meaningless. But it's okay. We found type token ratio is hard again. This is like, yes, this is wisdom from the 1900s, and it's still true in this day and age. Morphologically rich languages are hard, which is nice because I like them. But well, it's fun to see it pop up everywhere. So what we would have liked to do is just really scale this up and just evaluate more pairs, because it really isn't a lot of data, but training these systems is expensive. So if you have too much compute and want to do this, hell yeah, go for it. Keep me in the loop. I'll be curious to see what happens. Better models might also perform differently. And yeah, don't use it as a great measure for everything, but think about the concept. And I think with that, it's time to segue into discussion. This is a picture of me on my birthday last year riding an office chair down the street.